All right, good morning and happy week 10. Happy December. Last happy Monday, I guess. I hope you all had a good Thanksgiving break, feeling refreshed, ready to tackle these last, 2 weeks of school, I guess, maybe. All right. I, I have something put together for a final exam. I don't know. It's so hard for me to write exams just because, I don't know, is this easy or hard? Um, it's difficult to gauge. So anyway, I have written this, and I was kind of wrestling around with what kind of problems. It's going to be pencil and paper. So this is what I've written so far, and this is kind of like what I think you should study. So regarding the final, I've got a couple sections and questions. So one will be like basic concepts. So we covered data types, math operations, Boolean logic, things like that. And then writing functions in Python. So I will ask you to write, short little functions. So my intention is to not make it crazy hard, but you'll have to kind of think about it. And this is always the hardest one, because inevitably somebody writes a bit of code and I have to stare at it, and I'm not sure if this actually will work or not. So there's a balance between making the question too easy, where everybody gets it right, and making it too complicated, where now I have so my goal is when I'm grading this, I can read it and just know whether it's going to be right or wrong. But if you make it too complicated, then somebody will write, you intend for the question to be answered in 2 lines of code, but then somebody writes 20 lines of code for a simple thing. And then I'm like, is this technically correct or not? And I don't know. I don't want to be you're going to lose all your points if you write 20 lines of code for a 2-line solution, what should have been 2 lines. But I do feel that's not it's probably not a great answer, but I don't know. I got to think about. So anyway, please try to keep your solutions short and correct. It's much easier grading problems when they're correct than when they're wrong, and trying to figure out, is this worth some partial points or not? So I'm slightly dreading grading this question, but I think I have to ask you how to write a function. I have to ask you to write a function. I feel that's, what kind of test is this if we're not writing functions? Okay, so a lot of these, there will be a mix of here's some code written, and please write down what the output is, and then others will be please write a couple lines of code. All right, and my hope is that the ones where I'm asking you to write lines of code, again, you should be able to just get away with writing at most 4 lines or something like that, okay? Where define function name doesn't count as a line, okay? That's 4 lines inside the code block there, okay. You should be familiar with the different data structures of Python, and the ones that are really important will be, the lists, strings, dictionaries, and tuples, okay? And you should know kind of when, the list versus the tuple, when you should use and what's possible and what's not. If I try to do, tuples this dot append, you should know that's going to result in an error, right? You can't append things to a tuple, stuff like that, okay? And then lastly, some stuff on NumPy and pandas, okay? And so you should be able to take a data frame, do some stuff with like modifying it, locating it, filtering, and maybe doing some group by and aggregating aggregate functions there. Okay, and that will be what I plan on doing. Okay, so notably missing being a pen and paper exam. I can't really ask Matplotlib questions. Okay, I can't do like, you know, data visualization questions and stuff like that. It's really hard to do on a pen and paper exam. Okay, and then so that's that. Reasonable practice, okay, I think is kind of like going through some of these, like the related things on DataCamp. Like if you're having trouble thinking of like your own practice problems, you can go to DataCamp, okay, and look at kind of the problems that they generate there and see how much you can do. Like, what if they didn't give you all of that starting code? Like, can you, right? Because a lot of times in DataCamp, it's just like, here's all of this code, and then here's the little blank that you have to fill in, right? And what if they didn't give you all of that kind of scaffolding? Can you still kind of do it? I don't know. Okay. I hope it goes okay. This is going to be like the first pen and paper exam I've done for this class. So I'll tell you this. My aim is for a median grade in the 80s. Okay, so if the median, my perfect exam would be median is at 85. Okay, and then Q3 is somewhere in the 90s, and Q1 is somewhere in the 70s. That's like kind of my or high 70s. So 70. If the distribution is set, Q1 is 75, Q2 is 85, and Q3 is 95. I feel like that's a perfect distribution. Okay. If things get like, if I write this overly difficult and somehow the median is below 80, okay, so if the median ends up like 81, I'll feel like, okay, that's fine. Okay, but if the median ends up below 80, then I'll probably choose to boost everyone's grade. And the way I do grade boosts is I just add points across the board. So like I'll just add 5 points to everybody's grade or something like that if something like that. So that's kind of my threshold. If the median ends up below an 80, I'll probably add some points. If I write the exam too easy and the median ends up being 95, whatever, everybody just gets an easy exam, so that's fine. Okay, but yeah, that's my target. I'm hoping this goes okay, and yeah, I feel like I had to switch to pen and paper just because the last time I did this and I had a take home, it became really clear. And well, I felt the influence of ChatGPT in submissions, and so and then I felt like, well, now we're no longer testing students' ability to answer questions, but testing students' ability to copy and paste a question into ChatGPT, which is not what we wanted. So pencil and paper. There's still. I'm still wrestling with the long-term implications of, ChatGPT's influence on, I don't know, introductory level programming. Like, at what level does your own skill, like when you go into the workforce, what level does your skill have to be where, I don't know, where it's like you prove yourself valuable and I'm not 100% sure yet. I think it's still kind of new, and we're trying to figure out where things are going. If you have an idea, let me know, because this is something I think the entire the entire industry is wrestling with. But anyway, okay. Do we have questions? Does this kind of make sense? Yeah.
So the object-oriented programming stuff?
The what?
The
Object-oriented programming? Yeah, I didn't put that in here, huh? So we'll I guess we'll leave it out. Yeah. You have it in your homework, and again, you know, it could be tempting to, you know, I feel like the poker problem is complicated enough that ChatGPT would have a hard time with it to just kind of copy. I don't know. Have you guys tried? I haven't tried it actually, so I don't know. But my goal, you know, my plea to you is like challenge yourself, okay? So and try to wrestle through and work with it. But yeah, I think I'm going to leave it out. I think again, the risk with all of these things is if I make a question too complicated, then the answers that I have to go through get too complicated for me to easily grade. So there's a balance there. We'll stick with what I've put on this handout here. Okay. All right. Then that's it. So this last week, I've just picked some miscellaneous topics that all of these are kind of like, hey, here's some cool stuff you can kind of do in Python, and if you want to explore more, this is where you can start looking. Okay, so we'll do that. Okay, and so today we'll look at stats models and scikit-learn, sklearn, and this will just kind of be like doing some very, very, very basic modeling in statistics. But yeah, I guess all of this week's stuff will not be on the final exam, okay? But this is all kind of like, well, if you're interested, you should take a look. Have you guys taken 101A yet? Regression? Okay. Have you guys made a linear model though in R? Like you've used LM? Okay. When did you use LM? In which class? What?
I don't know. Did it in class? It was just like.
Which class?
I don't think it was. I don't did it.
Oh, you didn't use it in class, but you've just.
Stats 20.
In Stats 20, you use LM. Okay. Well, great. When are you taking 101A?
Next quarter.
Next quarter. Okay, great. And you're also taking 102A with me? Maybe? Oh, okay. I guess you didn't get into my class. But, well, so, all right. Well, anyway, I don't want to poo on Python. Okay, I love Python, but I also just want to say, when it comes to just traditional linear regression, if you're going to just fit a classical statistical model, like R is way better. Okay, if you want to do linear regression, ANOVA. In my opinion, R is the far superior choice over Python. Python gets the job done, and you'll find a lot of people use Python for it. Okay, but whatever. Okay, I don't know. Maybe I'm just biased because I learned linear regression with R first, and I'm like, oh, this is great. And then I tried to learn it on Python, and it's like, oh, okay, it also works, but it's not as nice, okay? And in fact, this thing is like based off of R syntax anyway, so it's like, well, just use R then. But anyway, I don't want, again, okay. So when we talk about modeling data, basically we have data and we want a way to explain how did this data get formed, All right, and that's creating the model. And so one simple way is linear regression, which basically says you have these variables, you multiply the variable by a constant, and you have like 5 variables, you multiply this one by this constant, this variable by this constant, this variable by this constant, and then you add them together, and that's how you get your final output. So a classic example is like, what is the cost, like how much is your apartment's rent going to be, okay? And so that's the variable you're going to predict, and then so let's just assume it's like an apartment in Westwood. So neighborhood's no longer a thing because neighborhoods are big things. And then so you say, okay, well, how many bedrooms is it? How many square feet is it? How many bathrooms or whatever, okay? And then you're going to say, okay, you take the number of square feet and you multiply it by 10, and you take the number of bedrooms and you multiply it by 200, and you take the number of bathrooms and you multiply it by 50, and then I just completely made this up, so I have no idea, okay? And then you add them together. So like, what did I say? All right, so if you have a 2-bedroom, 800 square foot apartment, I don't know, you do 800 times 10, or 80, what? Okay, 800 times, well, 8,000, okay, maybe that's a little high. But okay, so you do these things, you multiply them together, you add them up, and you go, poof, that's our prediction for how much the rent is going to be. Obviously, if you have different neighborhoods, now you have to put in a neighborhood variable, right? Westwood, add 500 to the rent. If it's, Santa Monica, add another 500 or whatever. But if it's like, I don't know, some other city, some other neighborhood that we don't, I don't want to say anything terrible about, we'll just say, maybe subtract 200 on the monthly rent or something like that, right? Like if you're living, an hour commute away, maybe subtract more, okay? And so you can do that, and that's basically linear regression. How do you figure out your coefficients? You try to minimize the squares residuals, and how do you know if your thing's a decent thing? You have to check your assumptions, and you'll learn all of that in 101A. Yes, question?
Did you post this on?
Did I not post it?
I don't think so.
Yeah, okay. Beep, 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 beep. Okay. All right, so, previews of, you can tell me if you want something different. I went to a Python conference earlier this year, and then they covered like all kinds of cool stuff. One was, on Wednesday, we'll look at Scrapey. So this is like web scraping. You go to websites and you can kind of like scrape their data if you want. So we'll look at just an introductory example on Wednesday. Again, we could probably spend an entire week of lectures on each of these things and get more delve into it. And then another one is now we have interfaces between Python and these AI LLMs like ChatGPT. And so you do have to kind of sign up for a developer account and maybe put $5 of credits in your API account. But then you can kind of link your Python to, say, ChatGPT, and then you can kind of send text requests, and then it will send your responses back, which is kind of cool. And so I'll show that on Friday, and hopefully all of these things work. And hopefully it sounds interesting to you. I don't know. And then again, all of these things, if you're more interested, you can further explore. All right, so we're going to do just a minimal, very, 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 very simple linear regression example. One variable to predict X, output Y, okay? So X is 1, 2, 3, 4, Y is 2, 6, 4, and 8. And we're going to just create a scatter plot to plot this. So here are my coordinates, 1, 2, 2, 6, 3, 4, 4, 8. And we want to fit a linear regression model to this. So we want to fit just a straight line that summarizes our data as close as possible. So we'll make a data frame out of this. column X, column Y, okay? And then, we can ask Seaborn to plot this, and if you do that, it automatically fits a linear regression line along with confidence intervals and or bands, and it's just not. One is, if you only have 4 data points, you shouldn't fit linear regression, okay? You're gonna have all kinds of problems, but linear regression is just a result of plugging your values into a formula, so it will produce results, but definitely you should go back and say, I need to collect more data, okay? 4 data points is not enough. But anyway, if you wanted to fit a linear regression model, you would call stats models, and you're going to say, I want to predict Y based on X. And this is kind of actually based off of R's formula in syntax or notation, where you do something like Y tilde X. Okay, linear model where we have Y as explained by variable X. The command we have the package stats models, okay? And stats models has 2 ways of interacting with it, okay? The traditional stats models API, the traditional way you're going to interact with stats models is you have a matrix of X values and a vector of Y values, and you have them relate. And then the other is you can use kind of R's formula syntax, where you do Y tilde X, and that's going to be the stats models formula API. The convention is stats models API is SM, and then the stats models formula API is SMF. Okay, so right now the formula API we're going to call stats models formula SMF.OLS, ordinary least squares. Have Y as explained by X. Data comes from our data frame D, and that's that. And then you say, okay, well, what is this? Right now, it's just a linear model object, okay? And then the way it works is you take that model and then you fit it to the data by doing model.fit, and we'll store those results, okay? So the results are now the linear is a linear model regression results wrapper object, and you can call for the summary. And this is going to be the output. And so the output here is kind of like a summary table, like in, so you will see in 101A, after you fit your first linear model, you'll probably call model, summary on your model, and you'll get a table that's similar to this, although not exactly the same. And it just got a bunch of information, right? Number of observations, 4. And you have 2 degrees of freedom for your residuals, 1 degree of freedom for your model. Your R squared value is 0.64, your F statistic, all of this. Your P value, your F statistic is 0.2. And you have your coefficient for the intercept is 1. The slope coefficient for the X variable is 1.6. That's going to be your slope. Slope of 1.6, intercept of 1.0. These are your test statistics to see if these are significant or not. And both of these are big, so neither of them are significant. And that's because we're basing our model off of 4 data points. And that's that. That's how you fit a linear regression model. You have your matrix, your vector of X values, your vector of Y values, put them together in a data frame, and then you'll create a model, smf.ols, you do model.fit, and then you kind of get your results.summary. You want to add the line, you can do that. You can make this call sm.graphics, AB line plot. So stats models, graphic, there's kind of like a graphic section. They all use matplotlib, so you can kind of make adjustments to it, and there's your thing. So if I do this without the scatter, it's just going to show the line, I think. Actually, nothing even shows there. Yeah, it just shows the line, and if you want the dots, which probably you do, you got to kind of call matplotlib to add the dots. And so this is the dots, and this is the fitted line. Not very interesting, but you have that. I don't know if ANOVA table means anything to you right now, but when you take 101A or 101B, certainly you will make the ANOVA table. And so this gives you just information about the model you fit, how many degrees of freedom, and generally you definitely want more than 2 degrees of freedoms for your residuals. Like your model fails when you have only 1 degree of freedom for your, if you have 0 degrees of freedom for your residuals, your model completely fails. And then, if you only have 1 degree of freedom in your residuals, then it's everything's going to have a hard time being significant. So you generally want, 20 degrees of freedom for your residuals or something, okay? Anyway, this is what you get. You get p-values, f-values, and stuff like that. And then if you want to make predictions, right? So you can say, hey, I want to make predictions for x is 2 or x is 3, x is 4. You can do that. You put in a little array of x values, and you can say, hey, what are your predictions? And it says, okay, your prediction for 2 is 4.2, and your prediction for 3 is 5.8. Your prediction for that fourth value is 7.4. So it just produces outputs for the values of x that you put in. Okay. Let me give you your first view quiz answer, which is the letter B. B as in bear. Okay. All right. NumPy array notation. So this is the other way to interact with stats models, is you could just use arrays and matrices. And I would say this is, in Python, especially with sklearn, this is kind of how you fit your models. So basically, rather than doing y tilde x, which is based off of R's notation, you kind of create a matrix x. And so in this case, we need a column for the x variable itself, and we need a column corresponding basically for the intercept. So you're going to add a column of 1s. And so we use stats models add constant, and so now our x matrix has a column of 1s and then a column of the x values. Okay, so you have 1, 1, 1, and then 1, 2, 3, 4, and then now we're going to fit it to our model y, and we basically you now have a matrix beta, which really just consists of the terms beta 0 and beta 1, and so we can say x, which is this, and if you multiply beta times x, now, the beta 0 gets multiplied by the 1, so it's going to just be the same as adding beta 0 to everything, and beta 1 gets multiplied by each x, and you get that, okay? And so this is matrix notation. This comes up later, I guess, in 100C, which you'll take in spring quarter, or maybe you've already taken it, I don't know. That's a fun class. Okay. All right. So anyway, now we do statsmodels.ols. So note here, this is capital O, capital L, capital S, and that's when you're using the classical matrix API. You use capital letters. When it's formula API, it's lowercase letters. That's the general syntax. So now you say, hey, y is our output, x is our matrix of predictors, and then you say, hey, fit it, and then give me the summary. And it's exactly the same. It's exactly the same, except it says constant and x1, okay? You can also get this, so I don't know if this means anything to you right yet, but like in 100A, you'll derive this solution for ordinary least squares is x transpose x inverse, x transpose y. And if you wanted to do it that way, you could use Python's linear algebra and get the same coefficients of 1 and 1.6 right here. Okay, but anyway, that's what we have. So this is just just a random example where we can fit slightly more complicated linear regression where we're going to have a x term and an x squared term, okay? And I've taken this example directly from the stats models examples. And so our x term goes from 0 through 10, x squared goes from 0 through 100, and then the true coefficients is we have an intercept of 10, x coefficient of 5, and an x squared coefficient of 2. We're going to add some random noise, and we'll plot this, okay? So you can kind of see these values that we're getting plotted here, and we can try to estimate these coefficients, okay? And we're not getting great estimates on the intercept and x1 term, but we do have estimates there. The x squared term, we got 2.2. That one's significant, and we'll just kind of create a plot of this, okay? So, and we can create kind of confidence intervals for all of this stuff. So these are, and basically this is our fitted values, okay? So the true line is in blue, okay? And we have a bunch of kind of noisy data surrounding this. And our fitted model is in red dotted line, okay? So it looks kind of close, but again, the intercept is a little bit off. The true intercept was 10 and it predicted 16. And then as far as the x1 term, it's off by a little bit. Not by too much, and its estimates a little bit off, right? So the x, if you think about like the different controls for a parabola, okay? So your intercept slides the parabola up and down. The x1 term will slide it left and right, and then the x2 term, x squared term, makes it like more narrow or wider, okay? And so it has the x squared term, it has like the correct like wideness, okay? It got that correct, and it's just saying like the exact location of like how high up or how left right it is not quite right. And you can forgive that because looking at our noisy data, like you're trying to kind of slide the parabola into its correct location. And it's hard to estimate based on just kind of the noise that we have here. But that's what's going on. Okay, so that's stats models. So it works just fine. Obviously, if you wanted to use it to fit linear regression in the future, you should pull up the documentation, look at examples, and make sure you're doing a complete and thorough job. But I'm biased, and I think R does a better job of just fitting classical linear regression. But certainly, if you're in the workplace and you want to fit a linear regression model, and your company is like, we're Python only, don't bother with R, like you're gonna have to use this, okay? And it gets to the job done, okay? I feel like I've trash talked stats models this whole time. It's a good package. It's a good package. It gets the job done. Okay. All right. We got a bunch of stuff with scikit-learn. Scikit-learn is probably like the most popular machine learning package for, I guess, an assortment of machine learning models. And scikit-learn, it's just like if you're going to do, say, deep learning, where you're doing like big neural networks and stuff, then you'll use like TensorFlow, PyTorch, Keras, or something like that. Okay, but for everything else, where you want to fit like k-nearest neighbors, or or whatever, some random forest type model, there, scikit-learn kind of covers a lot of these things. Okay, We are going to import the iris data. Are you guys familiar with the iris data set? Okay, iris data set. So there's the iris data set is, I don't know, it's like 100 years old. Some poor person had to collect. Maybe it wasn't said that they had to do this, but this was like the joy that brought them thing in life that brought them joy. But they went out and they collected irises and they measured the length and the width of their petals and the stamens or standards. I don't know, petals and sepals, whatever. Okay, and based on that, we can classify 3 different species of iris. Apparently, there's like hundreds of species of iris. Anyway, we'll load this up, and the data comes in this document structure called a bunch. A bunch is like a dictionary, except the values are like data frames. Okay, so if you look at the data frame for the X data, you have this data frame with 4 columns. This is like sepal length and sepal width and petal length and petal width, because on an iris, yeah. So apparently, when you look at this, these little ones are known as the petals, and these things, the big ones, are known as the sepals. I would have just called all of them petals, but I'm not a botanist and I don't know what these things are, but now I know something about irises. And so we have sepals and petals, and we measured them, and this is their size, okay? And the feature name: sepal length in centimeters, sepal width in centimeters, petal length and petal width in centimeters. These are small, right? 0.1, so this is a 1 millimeter. I don't know. This guy had 150 of these irises to measure. Go to the botanical gardens and clip some flowers. They won't be happy about that. This is your homework assignment: data collection. And then we have labels: class 0, class 1, class 2. The species are Setosa, versicolor, virginica, and then you have a description, and it's this, because this came from Ronald Fisher's 1936 paper on that, and Edgar Anderson had collected this data. I don't know. Where's our reference here? Annals of Eugenics. Well, that's uncomfortable. All right. Here we go. Okay, so now we're gonna fit a model here. Okay. So one thing that you do in machine learning. So machine learning is, there's not a lot of thinking going on, okay? Because it's machines doing it, right? So I don't know. I don't know how thinking even works in the first place. But the way we do machine learning, right? So when you do your linear regression class next quarter, 101A, you're gonna be asked, like, is this model, how well does the model fit the data? And then it's not just I look at the table and look at the p-values, but you also have to look at, like, are the assumptions that I've made met? And you look at your residual plots and you're looking for no pattern in the residuals. And there's all of these things you got to think about. And that's probably why people didn't like statistics, because it required all of this kind of thinking and some judgment calls, and you say, well, based on all of my experience, I feel like this is not a good model or something. Machine learning doesn't have any of that. Machine learning just says, hey, we need to score ourselves. What are the predictions? What are the answers? how close are our predictions to the answers. If the predictions and the answers are close, this is a good model. If the predictions and the answers are far off, this is not a good model. And but if you only have one set of data, it's kind of like, how well did you learn? Like if I give you a practice test, right, a practice final, and you score 100% on the practice final, but then on the actual final you did really poorly, okay? Then it's kind of like, did you just memorize the answers of the practice final, or did you actually learn the stuff, okay? And so what you have to do is, if I give you a set of questions and I say, here's your practice final, one way to kind of learn this is like you can study, like you can split the test into two parts, and you can study one part and you can kind of like learn from that, and then you can say, okay, well, can I try out these other things? And then you test yourself there. And that's kind of what we do here. We do this train test split where we take the available data, we split it into different parts, we use part of it to, quote, train our model so it can figure out how to make predictions, and then we say, how well does it make predictions on the test data, okay? And so we use this function called train test split from sklearn, and so from our 150 observations, 120 of them go into our training set, and then the remaining 30 go into our test set, okay? And then we stratified our test data so that we have 10 from each of the three categories. And we're going to fit a k-nearest neighbors classifier. I'm not going to get into how k-nearest neighbors works right now, but basically, if you have two-dimensional data, k-nearest neighbors just, you plot your data here. And then you say like, okay, here's like if I put a dot right here, okay, right at my thing, the k-nearest neighbors just says, all right, look at the nearest neighbors and you count all of the, maybe I'll go down, okay, over here. So in this location, we have 4 nearest neighbors, 1 red, 2 green, 1 blue. Okay, so if these are my 4 nearest neighbors, I say, if I have a dot right at the point of this arrow, what color should it be classified? Okay, we say, well, looking at the nearest neighbors, 2 of them are green, 1 is blue, 1 is red, so green wins, and we would classify this location as green, okay? If it's over here, we look at our nearest neighbors, we've got, out of the 5 nearest neighbors, all 5 are red, this would get classified as red. If it's over here, we have our nearest neighbors are all blue, this gets classified as blue, so on and so forth. And basically each dot gets a vote, okay? And so if this is it, you have 2 green, 1 blue, or something. That's how it goes. K-nearest neighbors, it's not just a predetermined circle, but it's kind of like you adjust the circle so the circle only has 5 values in it or something. That's if you're using 5 nearest neighbors, or you adjust it so you have 7 nearest neighbors or something like that. Okay, and that's two-dimensional, and then it expands. I can't visualize it, but you can go into 3 or 4 dimensions, and you're basically drawing, this hypersphere in a higher dimensional thing, and you're saying like, okay, what are the points that are closest? And so that's what we do. We train it on the available data, okay? If any of these things have like missing values, like infinities or whatever, we're gonna make them and replace them with missing. And then Seaborn, I'm asking it to make a pair plot, and it is struggling. Okay, there we go. All right, so here's the same thing, but there you go. Okay. All right, so we're going to do k-nearest neighbors classifier. I'm going to use 5 nearest neighbors. All right, and we say do it. All right, fit it to X train and Y train. Now make predictions on the test data. These are the predictions. I can compare the predictions with the actual values, and it looks like it got it right. Here's a little error. Here, the train actual value was a 1, and here it predicted a 2, okay? Now, it's hard to kind of compare like this, so you create what's called a confusion matrix. And here it says, when it was 0, we got 0 10 times. When it was a 1, we predicted 0 0 times, 1 10 times, and 2 0 times. And when it was row 2, we predicted 0 0 times. We predicted a 1 1 time, and we predicted 2 9 times. So basically, in a confusion matrix, you want everything along the diagonal. Diagonal means you got it classified correctly. Things on the off diagonal are where you misclassified, and this is the one error that we made. Okay. I could say, hey, try it again. Maybe instead of using, so back here I said use the 5 nearest neighbors. What if you just use the 1 nearest neighbor? So you could do that by doing n neighbors equals 1. You fit the confusion matrix, we end up getting the same performance, 10, 10, 9. So 29 correct out of 30. You could try fitting it with 25 nearest neighbors, probably not a good idea. And here we're making more errors. We have 28 correct out of 30. And maybe we want to have a bigger thing. So here I tested it out with k nearest neighbors, 5 nearest neighbors, 1 nearest neighbor, 25 nearest neighbors. And you might wonder like, hey, should I try out 3 nearest neighbors, 7 nearest neighbors, 8 nearest neighbors, 10 nearest neighbors? What, You could do that manually. You can also automate it, and that's called grid search, okay? And grid search, you just basically say, hey, try out all of these different values for something like k nearest neighbors or whatever else it is, and mess around with that. Okay, so there's another option for k nearest neighbors, and that is you can have weighted k nearest neighbors. And the way weighted k nearest neighbors works is you say, okay, what are my nearest neighbors for this point right here? And you know what? The points that are closer, those get their votes count more. And the points that are farther away, though they still get a vote, but we're going to weight their vote lower, okay? And so that would be distance-based voting, okay? Or distance-based weights. And uniform is everybody's vote counts the same, right? And so you could kind of say hey, should I do 5 nearest neighbors with uniform weights or 5 nearest neighbors with distance-based weights? Should I do 8 nearest neighbors with uniform weights or 8 nearest neighbors with distance-based weights? What about 50 nearest neighbors with blah, 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 right? And so you have all of these different things to test, and you're I don't want to do this manually. Well, you run grid search CV, and you say, hey, these are the different values, combinations of values I want you to try. And you do that. We can have it do cross-validation, which says, the way we did this is we split it into, we had 150 available values, and we split it into, 120 and 30. But you might wonder okay, with these 30 that I got, this is how I'm performing. But what if I had split it this way, where the 30 values I selected were here? Or what if I got these 30 or these 30? And so we're going to do what's called 5-fold cross-validation, and we kind of just split our data up into 5 different segments, and each of those segments get to be the kind of the test set. So anyway, you do all of this. It takes a few seconds because it's fitting basically 100 different models here, and it's testing them all out. And you could say, hey, what were the best set of parameters? And it says the 13 nearest neighbors with uniform weights. That seems to have the best score. Not 100% accurate, but it made only 2 mistakes out of 100. I don't know, out of 150. I don't know, 100 out of 120 things. I don't know, made 2 mistakes or something. It's still making 1 mistake on the prediction set. But anyway, that's how it goes. All right, there were other models. We're out of time to cover them, so I won't. But this is just kind of getting started as far as sklearn, as far as looking at some of these things. Okay, how many answers do I need to give you? I need to give you 2 more. Okay, last 2 are C and E. C as in, is that right? C as in cat, E as in elephant for your last 2 answers. Okay, we'll wrap things up here. We'll see you guys Wednesday.